Hey, it's Nathan, and I'm just popping in at the beginning of this video to note that this is a correction of an older video. At this point, at the time of filming, this video was put out around like a year ago, but just recently, this person gave me this comment telling me that I did something wrong, which is great. I appreciate that. It makes me a better math person. It makes me able to make these videos better or explain more about where I was coming from when I put things on the board. So thanks to this person again. And yeah, if you want to see what the correction was, it takes place in the last section of the video. What I wrote and what I say do not match. But also, if you just want to stick around for a little blast of the past from me when I just passed 1,000 subscribers on this channel, then this video will show you where I was around that time on the internet back in Madison, Wisconsin. Anyway, see ya and enjoy the video. All right, so today I'm going to talk about a handful of things, which I'm going to put right over here. And yeah, if you want to skip to a particular topic, you can totally do that. Otherwise, I'm just going to get started and talking about this stuff. All right, so last time we ended on the fact that the real numbers is an example of a T6 or a perfectly T4 topological space. It's important to note, though, that the real numbers aren't special in this case. In fact, any metric space is going to be a T6 or perfectly T4 topological space, or a perfectly normal Hausdorff space. A lot of times in other fields, you might have a metric space just given to you, but sometimes you might not get a metric space for free. You might not be handed something that inherently is built from a metric. A question you can ask is, well, is this topology metrizable? Metrizability is the quality of a topological space being topologically equivalent or homeomorphic to a metric space. And so what that means here is that your space with its topology will be topologically equivalent to some metric space with the topology induced by some metric D. And what we mean by topologically equivalent or by homeomorphic is that there is a bijective function that is also two-way continuous. So when you map from your topological space to the metric space in question, that function is continuous. And when you use the pre-image map from the metric space to the topological space, that is also a continuous map. And so there are metrizability theorems out there where you can take different conditions on a topological space that are not necessarily just the axioms that are set in the T6 condition and get something that is metrizable. But we're not going to focus on that because the title of this video is When Space Does Not Have Distance. So we're going to primarily focus on non-examples or topological spaces that are not metrizable. And so in the first case, we'll talk about a topological space that's not metrizable, and it's very hard to kind of shove it into a metrizable box. But then in the latter two examples, we'll give some examples where you can sort of manipulate things and mod out by some extraneous information in order to get a metrizable space. Okay, so our first example, which is also in the title of this video, is the long line. So what is the long line? It's going to take a little bit of work to define what the long line is, but it should be doable. So first, we should answer the question of like, why long? One of the ways you can think about the reasoning for calling it a long line is that it's a space that is too big for a metric or a distance function, in other words, to make sense. So in order to go ahead and get at what it means to be a long line, we also have to define what it means to be a long ray. So the closed long ray is by definition equal to omega-1 crossed with the half open interval from 0 to 1. Where 1 is the open bit and 0 is the closed bit. This is just a set, but it's endowed with the topology granted from the ordered topology given from using the lexicographical ordering on ordered pairs that describe points in the long ray. So that's a lot. That's a little bit jargony and not great, but we're gonna focus on what omega-1 means and then sort of use visuals to give some intuition here. So omega 1 is an example of an infinite ordinal, and it's shorthand for a half-open ordinal set, which is just the set of ordinals from 0 to, but not including omega 1. So the way you can visualize this is that ordinals are like counting numbers with 0 adjoined. So we start with 0, and then we count to 1, and then 2, and then 3, and then 4, and then so forth, all the way up to, but not including omega 1. Now, omega 1 is the first uncountable ordinal. So the intuitive way to think about this is that there are as many things in the set that corresponds to omega 1 as there are real numbers. And so when we go ahead and cross that with the half-open interval from 0 to 1, not inclusive, what we end up getting is we get this sequence of unit intervals that are stitched together. Now, if we wanted to make the long ray open, we would just remove the 0, 0 point from the first unit interval. But the important thing here, and the important thing for wrapping your brain around the intuition for the long line not being metrizable, or there being no sense of distance on the long line, is that there are uncountably many unit intervals that are stitched together in the long ray. Now that we have the long ray defined and we sort of have a visual for what that looks like, we can go ahead and define the long line as this LL thing. I'm using the two intersecting L's because it just felt good to do LL for long line. But I've also seen it as like blackboard bold L, like this. I'm not really sure what is considered the common notation for the long line, but I'm just going to use the double L thing because it makes me happy. So the long line is equal to the disjoint union of an open long ray and a closed long ray, where the ordering on one of the long rays is reversed and the points on the reversed long ray are all less than the normally oriented long ray. That square union thing is important here. That's the symbol for disjoint union. And there are other ways to denote a disjoint union, but I'm just going to use this one. And so what that means is that instead of just unioning things together, we're going to force the sets to be disjoint and then union them together. And the way that we can do this is we take the first set, which in our case is the open long ray, and we take that open long ray producted with the singleton of 0, and then we union that product with the product of the closed long ray and the singleton 1. Now that's sort of a lot, but basically it just makes a line as you would expect it to be. So just to get a sense of what this looks like, it's going to look very similar to our long ray picture above, except for we're going to have two long rays going in opposite directions. And I've also just labeled the long line with some coordinates and some interval labels just to give you some ideas of where those products are coming into play and all that fun stuff. But that's essentially what the long line is. So the next thing to ask is, well, how different is the long line from the real numbers or the real line? So the main difference here is going to come from the fact that there are a different number of intervals in the long line and in the real line. So in the real line, we only have countably many unit intervals that are stitched together, whereas in the long line, we have uncountably many. And so how this looks visually is that if you laid the long line on top of the real line, eventually you would run out of real line and the long line would overtake it and continue on. With that being said, we should probably give some intuition for why the long line doesn't have a metric on it, or why the long line is too big to have a metric on it globally. Now, just as a preface for this, I don't think this is a proof. This is how I've thought about it intuitively, and it's gonna feel a little proofy because I'm gonna use a contradiction to sort of get us there, but most of the rigorous proofs that I've seen have actually used strictly topological qualities of each thing instead of assuming that there is a metric on the space and getting to a contradiction. So to continue, we're going to go ahead and assume that there is some metric d sub long line that goes from pairs of points on the long line to the real numbers, or the positive real numbers in this case, with 0 included here. And then instead of just thinking about any two pairs of points that you can find on the long line, we're going to think about distance from the origin of the long line. So we can go ahead and define another function that is just d sub long line of 0, x, where that x will be filled in by another point that is on the long line, and that will be sent to the positive real numbers with 0 included. So it's important to note here that this function has to be increasing. If it's not increasing, then we can have something that is closer to the origin that is just as far away as something that is farther out from the origin. And that doesn't make sense in terms of metric, because the whole point is to give a notion of differing distances from a point in space. So I'm going to visualize this by drawing the cross of the long line with itself, which results in this border, which represents that omega-1 region that's not included in the long line, but the long line goes up until that thing, but in plane form. So the way that you can think about this function is that we've already picked our point on the horizontal long line. Now we just need to pick our point on the vertical long line. And then since the long line will overtake the real line in both directions, there is some point in the space of this long line plane where we will exceed the bounds of the real numbers. So this geometric intuitive argument goes as so. Pick some point on the vertical long line that is outside of the real bound. So something that is far enough away that it's farther away than the real numbers can reach. Then call that point A. Once you've established A, then there must be a point that falls on the bound of the real numbers, and we'll call that B. But B is going to be R far away from the origin, which means that once we're at B, we've used all of the real numbers as outputs of our distance function. And so that means that there exists some C somewhere in between the origin and B that will have the same value as our distance from the origin to A, because in between the origin and B, we used all of the real numbers and 0 in an increasing fashion. Once we pass B, we don't have any new real numbers that are bigger to set as the distance value. And that doesn't make any sense because C would be less than B, which is less than A. So we would expect the distance from the origin to C to be less than the distance from the origin to A. Then the d sub long line function is not a metric, and since we didn't assume anything about the d sub long line function other than that it was a metric, there's no metric on the long line. Okay, so the long line gave us an example of a non-metrizable space where we couldn't force the long line into this weird state of having a metric, or at least there wasn't an obvious way to do that. The next two examples I'm going to go over sort of have a way to make a metric work on them. Our first example will be anything that is a finite topology that is not discrete. And so what discrete means here is that topology is discrete if that topology is just the power set of your space, where the power set is just the set of all subsets of your given space of points. So in this example, we can have these 3 points A, B, and C, and have it so that A and B are not separated points. And so since A and B aren't separated points from the metric space point of view, there isn't a way to assign a metric to the space that will keep A and B not equal to each other, but also not separated, as in having distance between A and B equal to 0. But there is a little bit of manipulation we can do to this topological space to get a metrizable topological space, and it has to do with the topologically distinguishable pseudometric. And so what the topologically distinguishable pseudometric means is that the pseudometric between A and B will be equal to 0 if A and B are not topologically distinguishable, and the pseudometric of A and B will be 1 if A and B are topologically distinguishable. So we can go ahead and use this pseudometric to define some equivalence classes between points. And that leads us to this new image of this topology when we mod out by those topologically indistinguishable points. And we get this 2-point topology that has a metric which is just the discrete metric, where d of x and y is equal to 0 if x is related to y, and d of x and y is equal to 1 if x is not related to y. So our second example is a little bit more general, but other pseudometric spaces tend to have properties like this where we can mod out by 0 and recover a metrizable space from something that formerly wasn't metrizable. One of the places you can see this more clearly is on the space of functions from a space X to the real numbers. So in order to make this a pseudometric space, we can go ahead and take some base point, we'll call it X sub naught, within the space. And we'll go ahead and define the pseudometric of f and g, where f and g are functions on this space, equal to f of x naught minus g of x naught, and then take the absolute value. So just to see that this operates in a very similar way to our first example above, we can take f equal to 3x plus 1 and g equal to negative x plus 1, with a base point defining the pseudometric of x naught is equal to 0. So then f of x naught is equal to g of x naught, which is equal to 1, which means that the pseudometric evaluated on f and g here will equal 0, but f is not equal to g. So in the topology that's induced by this pseudometric, f and g are not separated points. And so we have an instance of a space that is not metrizable, but when we look above and we think about modding out by this 0 relation, we can do a similar thing here in order to get a metrizable space as well. So in analysis, it's actually really common to use these sort of like mod out by 0 relations in order to produce nicer spaces that can be metrizable, or where a metric makes sense on them, in order to more efficiently work with the mathematical objects that you're given. In measure theory, you can also think of this as equivalence under the almost everywhere property. If you're familiar with some measure theory. If not, maybe I can talk about that later. But yeah, that is some instances of when a space doesn't have a strict notion of distance, and I hope that you enjoyed learning about that, or hearing me talk about it, or not the pictures on the board. Anyway, that's all I have for you today. If you did enjoy this video, and if you made it this far, you can give this video a thumbs up and subscribe for more mathematics stuff on the internet. I've seen that a lot more people have decided to hang out and watch these things that I've been making lately, and I am super, super grateful for that, because it's something that I enjoy talking about, and I get to talk about it on the internet, which is cool, and people generally respond well to it, which is awesome. So I appreciate that. But yeah, anyway, thanks for watching again. I am Nathan, this is Chalk, and I will see you next time.